Okay. So the last thing we need to talk about, and actually remember the part on your test where I said I'm going to ask you questions about those 3 subatomic particles, which one's negatively charged, which one's positively charged. Some are easier than others. But one of the things I could ask you is which subatomic particle gives the atom its size? And it's the outside one, it's the electrons. So that's why actually they say that most of an atom is empty space. It's like 99.99% is basically space. There's nothing there. Is it outer space? There's nothing there. So volume is a function then, when we talk about how big an atom is, it's going to be a function of the radius, basically from the nucleus out to kind of the edge of where the electron cloud is. So kind of think of it that way. Okay, so that's the nucleus here, electrons creating not necessarily a spherical, because that's the S-types electrons, right? Otherwise, it can kind of be dump-shelled shaped or kind of weird shaped when you get to the P and the D-type electron orbitals. So how big an atom is, that's what we're going to talk about. And you'll have a little section with probably 4 points on your test to say which atom is bigger, basically. So here's the catch. If we take the group A elements, okay, so this says just the group A elements. Now, one of the things, and I didn't mention a minute ago, but when I said for the periodic table, you need to know the group names. There's like 4 of them. You need to know the group names. You also need to know the JAG, right? That little stair-step thing, and that separates the non-metals from the metals. That's a player. Actually, in Unit 3, we're going to kind of still talk about the non-metals and the metals. Okay. The other thing about the, I guess that's one of the big things. Oh, and we talked about group B elements, right? Those are the kind of the indented ones. And then there are the lanthanide and the actinide series, your F block elements. So anyway, so if you take just the 1A, 2A, and then the 3A through 8A, squish them together, they look like this. Okay? These are the group A elements. It's weird. We took out the B's. So you can see that actually the easy trend to me is when you go down, they get bigger. Okay, when you go down a different period within the same group, they get bigger. That's cool. That's electron cloud get bigger. A whole crap load of more electrons. For instance, between potassium and rubidium, a lot more electrons. Okay, between germanium and tin, SN is tin. That's another favorite one, right? Okay. It's bigger. But the trend in the same period, so within the same group, increases going down. Within the same period, it's a little bit counterintuitive, which means it's a little bit backwards. So you saw a minute ago that, let me pick what color do I want to pick? Okay, so the trend here is increasing, okay? But to increase across the period, you have to go from, I say right back to left again. That is where size increases. INC for increases. So if we pick on the neon, fluorine, oxygen, nitrogen, carbon, boron, beryllium, and lithium, going from right back to left again, they're getting larger. Which you're like, dude, electrons make the volume, and we know neon, if it's neutral, has 10 electrons, and lithium, if it's neutral, has 3 electrons. You're like, how come lithium can be bigger than neon? So I'm going to have to kind of explain that. When I explain how come it gets bigger if you go backwards like that, if you don't quite understand it, that's probably okay. But you need to know, size-wise, that across the period it gets bigger going from right back to left again. So this is another chart just to kind of go ahead and give some numbers underneath it. Okay, so those numbers are in, they're radii, they're atomic radii. So if you go from the nucleus out to the edge of the electron cloud, how big, you can calculate the volume given the radius. So these are in meters, but they're picometers. Picometers, aren't those just adorable? Okay, so anyway. So again, you can see from fluorine to lithium, lithium has 152 picometers as the radius between the nucleus and the outside of the electron cloud. Okay, fluorine is 71 picometers. Okay, it's got 9 electrons versus 3 electrons. But you clearly see the thing going down. If you're in the group going down, it's going to get larger. So I don't think this video will play. I didn't. Okay, that's okay. You're not missing much. But what that video would have told you is sometimes, you know, how do we get the radius of, because we can't really even see atoms. Individual atoms, it's kind of a tricky thing to see individual atoms. Okay, so oftentimes to get the radius of an atom, remember we said that, well, let's pick on these two chlorine atoms. We said that chlorine's great because it's one of the 7 elements that like to run around as a diatomic element. Remember Hoffer-nickel? It's the coal in Hoffer-nickel. I guess that was another thing we talked about, both in Unit 1 and Unit 2. The 7 diatomic elements, 7 dilithiums. So one of the things that we can do is actually measure the, we can sink our teeth into a Cl2 molecule and look at that collectively and then go ahead and get the radius. Okay. So now we're going to talk about the whole increasing going down, okay? The size increases, the size of an atom is governed mostly by its electrons, well basically by the electron cloud, dictates how big an atom is. Okay, so if you're going down, for sure you're adding on a whole more crap load of electrons as you loop back around, okay? The periodicity of the periodic table, you know, so if you kind of pick on sodium to potassium, sodium has, let's see, 11 electrons if it's neutral. Potassium has 19 electrons if it's neutral. So you picked up 8 electrons, so it just is bigger. So in order to explain the whole period thing, the whole atoms getting bigger from right back to left again, we need to talk about kind of what's going on in the atom with regard to attractive and repulsive forces. So looking at attractive and repulsive forces, they look like this. So I'm going to draw a little atom down there at the bottom. Let's pick on blue. Okay, so this is my nucleus of my atom. I'm going to put, let's go ahead and make it, let's make it lithium. So I'll put 3 protons in here. I don't know what the most natural isotopic form of lithium is, but I'll put some little circles here. These can be my neutrons. Okay, let's go ahead and, so this would be, let's see, can you see where this actually would be mass number? A is the symbol for mass number. Actually, A here would be 3 protons plus 4 neutrons. You buy that? Look on the mass number of 7 there. Okay. So if it's neutral, that's lithium. And if it's neutral, then we need to have 3 electrons out here. So I'll go ahead and draw my little 3 electrons. So there's a certain size associated with that lithium atom. And again, it's the this isn't drawn to scale because remember those electrons are just way out here, right, compared to the nucleus. So the attractive forces look like this. The attractive forces would be each electron wants to come in towards the nucleus. Okay, those are attractive forces. The repulsive forces are here. Each electron wants to repulse from each other. Okay. That's repulsion, attraction. Okay, so we have 2 things going on. Basically, it wants to come in and be small, okay, because electrons will be pulled into the protons, and it wants to fluff out and be big because electrons are like, hey, I don't want you. I'm going to make myself big. Okay. So since as we go, and I'm going to switch gears, I'm going to go from left to right, because usually we read things from left to right. We read sentences, we work problems, we write chemical equations from left to right. Okay? So as you go from left to right, okay, it's getting smaller. Okay? So since it's getting smaller from left to right, there must be something going on with regard to increasing attractive forces, increasing attraction from left to right. And I'm going to introduce something called effective nuclear charge. And what you do get, if you're in the same period, going from left to right, kind of hopping along the periodic table, what you do get in the next box to the right is you pick up a proton in the nucleus. So bringing into this concept of effective nuclear charge, basically you are increasing the attractive forces for electrons to be attracted to the nucleus because there's protons there, okay, and that makes it smaller. So I'm going to have to kind of tell you why, when we go across from left to right, why you pick up a proton and it gets smaller. You also pick up an electron. You would expect more repulsion of those electrons out there. And there is more repulsion, but the attractive forces are what dictate the size, what make it smaller from left to right. So this just said, I know that you're picking up a proton, which increases the attractive forces. You're picking up electron, which increases the repulsive forces. But it must be the attractive forces that are winning out. A lot of forces going on in this universe. Okay, so let's work a problem. And this is like, kind of like your homework, and this is kind of like what the test will be like. I think for the test, I'll only give you a pair. Here we've got 5. And sometimes, and these have been picked just so that we can actually work this problem. Sometimes somebody give you 5 and you're like, I don't know, it's kind of hard to tell. But I'll show you why just using the arrows, increasing, going down the same group, the atom gets larger going down the same group. And if you're in the same period, it gets larger, and you want to get larger, you're going to have to go from right back to left again. Just those 2 trends, we can figure out what these are. Now, on your test, if you have these, one of the first things I would do is to snag that periodic table, okay, and circle those 5 on your periodic table and look where they're at on your periodic table. Okay, things will fall into place a little better. So those 5 on the periodic table are located right here. So I'm going to go ahead and draw the arrows. Let's pick purple. Okay. So size increases. The arrows are how size increases. So size increases going down. Okay. And size increases going from right back to left again. Size increases. So in other words, I'm going to put small up here. I'm going to put small down here. You buy that? So here in a minute when I work this, or when we work this, how many people, I'm going to ask you to raise your hand. How many people think fluorine will be the largest? How many people think fluorine will be the smallest? You're very right. How many people, okay, let's pick on, I'm going to choose orange. I just want you to focus on phosphorus and sulfur. How many people think phosphorus is larger? Me too. See, that's it. That's just it. Very good. You guys will do great. Okay, perfect. So there's different ways to kind of think through this. I'll show you, and you guys are right with regard to the smallest and the largest. Fluorine's going to be the smallest. Cesium's going to be the largest. Okay, so can you see where, and you guys already told me, so fluorine's the smallest, and you guys told me that actually then it'll be sulfur and phosphorus, right? Don't mess that up. Like, it's okay if you do mess it up. Sky will still be blue. But sulfur is smaller than phosphorus. Cool. But does it make sense that calcium is larger than sulfur and phosphorus? Because calcium is in the next period. Good. Very good. And then last but not least, is cesium. Okay? So that's it. So like I said, on your test, I'll just give you a pair. Cesium. Oh, you're right. There we go. How come I have CE or CS?
Oh, wow.
Why? Syria. I think that was just a.
I'm just gonna see us. Period 6.
Yeah, but where's my CE? Oh, okay. I think that was bad. This, okay? Okay.
Oh, there is a.
Oh, there is a CE, yeah, it's
All the
it's
way
an
there,
actinide. It's an actinide. Okay, yep, there is. The CE is about here. It's also in period, it's also in the same period as cesium. CE is right here. Good. Well, that's not as bad. Okay, very good. And here actually are their atomic radii, which just means the radius of the atom. So you're like, how could you get a radius of an atom? Well, you go from the nucleus out to the electron cloud, edge of the electron cloud. So these are
I'm guessing
atomic
that
radii.
is supposed to be CS though, even though it says CE.
Yeah, me too, me too. CS. It's like, why not stay consistent, right? Okay. So for every rule there are exceptions. And notice that we limited it just to A group. So I'm counting on you guys knowing your periodic table. We have 2 columns over here that are A, and then we have 6 columns over there that are A. Okay. The other ones, the B group, are called transition elements or transition metals. And this is how, these are 3 different periods. Let's see, the blue period, and actually it goes, the 6th, the 5th, and the 4th period. You can kind of see where it doesn't stay. As you go from right back to left again, it doesn't always get larger. You can see kind of the exceptions. They're not too bad as exceptions go, though. The exceptions are kind of here-ish, aren't they? All right. So to kind of wrap it up, I want to explain that whole attractive force increasing as you go from right to left. Or, excuse me, increasing as you go from left to right, because it gets smaller, right? Okay, so there's this thing called effective nuclear charge. An effective nuclear charge of any atom can be calculated. It's a little subtraction problem, okay? And it's calculated like this. And it's cool. It's got this kind of cool Z star is equal to the number of protons. Oops, better make that a positive. Okay, the number of protons, and from that you subtract, I got this right, I usually bring my little cheat sheet. From that you subtract the valence electrons. No, you subtract the I think the word is inner. I think your book uses inner electrons. Okay. And that is your effective nuclear charge. Okay, so I'm going to do a couple of examples up here on the board. Calculate, it works well if we do it for, let's do it for magnesium and for phosphorus. It's cool because magnesium and phosphorus are on the same period. Which one's larger? Magnesium is larger. Very good. Okay. So we've been talking about here what a magnesium atom would look like. Okay, so it's atomic number 12, so it has 12 protons. I'm not going to write the little protons, but okay. And if it's neutral, which this one is, it has 12 electrons. The first 2 electrons are in the 1s. The next 2 electrons are in the 2s. The next 2 electrons are in the the next 6 electrons are in the 2p. All I'm doing is finding homes for these 12 electrons. Okay, let's see, then you would tell me 3s, okay, and I peter out with 2. We good with that? Okay, so the superscripts add up to 12. Okay, we talked about inner electrons and outer electrons. Valence electrons. Doesn't that almost seems like it should be a vocab word, so I don't know. Valence electrons, there are 2 there. Let me go ahead, they're so special, I'm going to do this. Those are my 2 electrons in the 3s subshell. So according to, and these are my inner electrons. So according to this, the effective nuclear charge is 12 minus, let's see, 10
Mm-hmm.
equals 2. I'll put a 2 plus there. So basically, the pull of these that these exert is actually a plus 2. Okay. All right, so let's look at aluminum. And aluminum is atomic, no, I said phosphorus. Let's look at phosphorus. It's atomic number 15. So there are 15 electrons that we need to find homes for, and 15 protons here. Okay. And it has a similar structure to this. Actually, we're going to see the cool thing about this, it's in the same period, it's going to have the same inner electrons. So let's knock them out. 1s2, 2 electrons in the 2s subshell, 6 electrons in the 2p subshell. It'll be 3s2, and then it peters out in 3p. And if I skip across, this is where it's a p block, and I'm skipping across p block. You see where it's 3p3. Dun, dun, dun. That's how I usually use the periodic table. So these are inner. Okay, these are valence electrons. Since they're so special, let's go ahead and make little pictures of them. I got 5 valence electrons, eh? Okay, so my effective nuclear charge is now 15 protons. From that, we subtract the same 10 inner electrons for an effective nuclear charge of a +5, or 5+. So here's the deal. I'm going to circle my effective nuclear charge of +2 and my effective nuclear charge of +5. So here's the deal. I know this seems kind of strange, but it's really how it works. Each one of these 5 electrons independently feel a +5. They each independently feel a +5. You're like, really? I'm like, yeah. So can you see basically where that phosphorus atom, each electron's like, oh yes, I think I want to come to the nucleus. Basically, it's so much, this is much stronger. I'll go ahead and kind of do it this way. If we use the size of the arrow to show what sort of attraction we have, it looks like that, and this one would look like this.
So is that actually why one's bigger than the other?
That is why one is bigger than the other. Yep. That makes this one smaller. It's effective because of effective nuclear charge. This one is actually larger. That's it.
That is awesome.
I think that is too. Okay. That bit about subtracting these inner electrons, subtracting that from the number of protons, okay? This actually is, we call this a shielding effect. Okay, we basically have the same shielding in both. Okay, they're in the same period, they have the same inner electrons. All right, so your homework looks like this. 82, 84. Not too bad. Now, the thing about it is, and I think you guys sound like you're really caught on, okay? But if you want some practice, remember you can do the one before it because the answer's in the back of your book. But again, in this case, you just have a pair, this is like what your test is gonna be like. And in here, it's kind of like, because of C's in the end, or, yeah, the other one's cerium, C's in, okay. Here, again, I would find them on the periodic table, circle them, and so you can kind of sort them out. Okay? All right.
Yay.
Yay.